Okay, so we're looking at the general multiplication rule, but in a different sort of light here. When we talk about complements and conditional probability, specifically the complements component, we're really talking about the idea of using the event that you're not interested in to help you figure out the probability of the event that you are interested in. All right, so we're going to focus on a particular case, the case of at least one, right? One or more, also known as greater than or equal to 1. All right, so we have this rule here where the probability of at least 1 is equal to 1 minus the probability of none. All right, so in terms of a setup, I can go kind of a simple kind of a diagram here. So let's say you have some random variable x that has outcomes 1, 2, 3, all the way up to, we'll call it n. And then we have probabilities that go along with those values. All right, so p of x, all those probabilities. So I'd have the probability of the event 1, the probability of event 2, the probability of event 3. Oh, I missed an important one. 0. Probability of event 0, all the way up to the probability of event n. Kind of defeats the purpose if I don't get 0 in there. All right, so if I want the probability of at least 1, all right, so I'll show you what at least 1 is. At least 1 is all this stuff. Because that's the case of 1 or more. All right, so this is at least 1. All right, we can think of this as none, right? 0 is none. If we look at this whole set, and I'll make it kind of a table out of it. We look at this set as the total set of possible outcomes, then the sum of all of these probabilities, right, the sum of all of these probabilities, remember that funny looking E is really just representing sum, it's capital sigma. Sum of all those probability values should be equal to 1 because we've accounted for everything. All right, so if we just figure out the probability of the thing that we don't want, which would be the event none, then what would remain when we subtract from 1 would be the probability of the thing that we do want. So it's a little bit of the theory. It's in a lot of ways a little tricky to get your bearings with or get kind of a good understanding of, but when you start getting into examples, it starts to make a lot more sense, right? So looking at number 1, find the probability of tossing at least 1 head in 2 tosses of a fair coin. So if we use this model, probability of tossing at least 1 head. All right, by rule, that would be the same as saying 1 minus the probability of tossing toss 0 heads. All right. Now, it's 2 tosses of a fair coin. So you got to think about what it means to not get any heads when you toss a coin twice. It means you got tails twice. All right, so the probability of getting a tails and then another tails. All right, because they're independent events, the idea is that I can flip a coin 30 times. On the 31st trial, no matter what I got on the first 30 attempts, the probability of getting heads is still 1 out of 2, and tails is still 1 out of 2, because it's not impacted by any other events occurring. All right. So this is the same as saying the probability of getting a tails multiplied by the probability of getting tails, which is a half times a half, which is a quarter, and 1 minus a quarter is 3/4. All right, all stuff that you can do on a calculator if you want, but in this case the numbers are kind of nice, so it wasn't really, wouldn't say it was overly necessary. However, you still have that ability if you want. All right, you could also create a sample space. You look at it and say, all right, well, what are my possibilities? I could have a heads and a heads, if we use a sample space. Heads, 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 tails, tails, heads, tails, tails. We want at least one heads. Well, that would be this one, and this one. There's 4 possible outcomes, 3 of which have the thing that you want to have happen. So 3 out of 4. And you say, well, I'll do it that way. Yeah, but what if I tell you to flip the coin 15 times? You can't do it the same way. Right? So you gotta make an adjustment. All right, but what we were essentially doing here is figuring out the probability of just this one event. That's what this is. Knowing that these probabilities, all of them together, have to add up to 1, we can figure out the thing that we don't want, that's one computation, subtract it from 1, then we would get our answer much quicker. All right? So 3 tosses of a fair coin. You're going to see a lot of similar computations when you're dealing with the same scenario, or at least in the early goings. Then it starts to deviate a little bit. All right? So the setup is going to be the same for numbers 2 and 3, at least in the early goings, like I said. So you're tossing a coin, this time 3 times. That's telling us that we're going to have 1 minus the probability of getting a tails multiplied by the probability of getting a tails multiplied by the probability of getting a tails. So 1 minus a half times a half times a half. A half times a half times a half is shockingly not 1 over 6, it's 1 over 8, because 2 times 2 is 4, times another 2 is 8, so 1 over 8 gives a result of 7/8. All right. Now, obviously, the sample space approach is going to be a little bit lengthier if you wanted to do it that way. So you start kind of shying away from that sort of thing, especially when you get to something like number 3, where it says to do it for 37 tosses of a fair coin. It's like, that's going to be crazy. However, it's actually not that bad once you realize that the number of multipliers of 1/2 corresponds with the number of tosses of the coin. So 3 tosses gave 3 multipliers, 2 tosses gave 2 multipliers. So you got to figure 37 tosses is going to give 37 multipliers. So this is really just going to be, you can kind of cut to the chase here, 1 minus, do you want to write 1/2 times 1/2 times 1/2 times 1/2 times 1/2 37 times? Probably not. So let's write 1 over 2 raised to the 37th power. Now it's going to give us a pretty gnarly looking decimal, but it is what it is. The other option would actually be to raise each part of that fraction to the 37th power, get some monstrous number. But here we could say, we could just put this whole decimal in there. Because if you start over rounding it, then it goes to 1, and that's misleading. Right? Because it's not guaranteed that you're going to get at least a heads in 37 tosses of a coin. It's a pretty solid chance. I mean, it's almost guaranteed. It's virtually guaranteed, but it's not guaranteed. Guaranteed would be like you would stake your life on this, right? So, and that's not what we would say, unless you get a probability of 1. I mean, it's not worth risking your life over, right? So that's the whole thing. When we say a probability is 1, we're saying you would bet your life on it. All right. This is like, are we going to take that chance? Maybe some people would, but I'm not calling this one. I'm not telling somebody that it's an absolute guarantee that it's going to happen. I'm not ready for that. All right. So what I would say is, and I don't want to say 0.9 repeated because I got that 3 at the end there, so that's dangerous. So I'd actually just write the whole decimal out. So you saw as I was blabbing on here, instead of writing the decimal out, I just did a quick screenshot. which is why I've been encouraging people to save their Desmos work, because you know it could be a matter of just submitting your computations. Number 4, now we flip the script here a little bit, and we say a die is rolled 6 times. All right, so, oh, I thought I still had the other thing copy-pasted, or copied anyway, in order to paste. I'll just rewrite it. I just kind of looked into the future, saw myself copy-pasting the previous line of writing, and saw myself erasing almost all of it. So why not just rewrite it? All right, so roll at least 1 4, and that would be 1 minus the probability of rolling no 4s. Well, we got a little die here. Look at that. Well, here's the case of getting a 4. That's the thing we want, which means it's all this other stuff that we don't want. All right, so the probability of getting a 4 is 1 out of 6. The probability of getting something that's not a 4 would be 5 out of 6. All right, so just kind of hold that piece of information in mind, because I want this to happen 6 times. So I would actually be thinking, all right, probability of not getting not a 4 multiplied by the probability of getting not a 4 multiplied by the probability of getting not a 4, not a 4, 1, 2, 3, 4, I need 2 more, throw one over here, and not a 4, 1 minus all of that. Now if you're rightly thinking, well, do we have to write all that? The answer is no. What you should write instead is 1 minus the probability of getting not a 4 raised to the 6th power. In which case it would be 1 minus, we know the probability of getting not a 4 is 5 out of 6 to the 6th power. Then the rest goes into Desmos. All right, so 1 minus parens 5 over 6 raised to the 6, raised to the multiplication, no, raised to the 6. Now you see here, you could go decimal form, but it also gave us the option to put it in fraction form. So I'm going to do that. I'm going to tap on that little fraction icon, because now I don't feel so bad about writing the answer. I don't have to worry about the screenshot. I just write this, 31031 over 46656. So if you have a computation that gives you the option for a fractional answer, why not just grab that? The previous one, you'd say, oh, why didn't we do that there? The previous one didn't give me that little icon. It wasn't presenting me with a fractional equivalent. All right, we could have come up with one. It would not have been pretty. All right, so it would have involved most likely scientific notation. I can double check real quick. 2 raised to the 37th power. Yeah, it would have involved scientific notation. The number would have been too large for Desmos to really present in a reasonable way. All right, so a couple of different problems with different twists on them, but they're all ultimately related to the same concept.